All right, so before we kick off, so here's the sort of the fun part for tonight. I feel like it's a little bit Fight Club, like I have to explain the rules of it here, both for the benefits of our speakers and there's a couple things as the audience you should be aware of. So lightning talks, the idea is they can vary in length. For tonight, we've picked 8 minutes as the time, which is going to be interesting. So on the low end, we have people with about 7-8 slides. On the high end, I think we have 34 slides. So if you guys remember the Micro Machines man from the 80s, I'm kind of expecting to see that. I think that covers everything. I will have the kitchen timer running for 8 minutes. So it can be the bad guy, not me. It has no mercy. If it goes off, you've got 2 sentences to wrap it up and then go on. If you get cut off on your talk, I think we've got about an hour of content, so we could probably come back to whoever gets cut off at the end, time permitting. So, all right, I think that's it. So Bryan, you're up.
All right, thanks. I'm Bryan. So we had this guy from Progressive here earlier this year that gave a really interesting talk about lots of things. And one of the things he said was that some folks still like SAS because many of their methods just work on arbitrarily large data. They may run very slowly on those data, but they just work. Whereas conversely, R is kind of fundamentally an in-memory computing system, which is true, kind of. There turns out to be tons of out-of-core. Out-of-core means not running in primary computer RAM, but maybe RAM augmented with disk or something else. And there's a lot of packages that actually kind of do out-of-core computing. FF by Dan Adler was probably the first really amazing programmer, Adler. Then Mike Kane and Jay Emerson did Big Memory, which I helped out with when Mike was a student. Tom Lumley, of course, has Big LM and Big GLM. More recently, there's tons of stuff like from our studio, SparklyR, and other external connectors to external large-scale processing systems that can work on data that's too big to fit in RAM. Simon Urbanic has a package that's explicitly designed to chunk data up called iTools off a disk. You can manually chunk problems up, and there's tons of others, I think. There's lots of ways to do this actually in R. But one thing about all those approaches that I mentioned there is that they're specialized. They'll cover certain very specialized subsets of problems very nicely, sometimes with extraordinarily good performance. But they're not generalizable to arbitrary problems. They work for specific important problems, and they tend to work very well for those problems. But they don't work in general on an arbitrary problem with some package with an arbitrary piece of, maybe you've got compiled code or whatever, and you want to run a huge problem, and it just runs out of memory. So Mike and I, back in 2010, when Mike was just graduating, we worked on a package that's been sitting around for a long time, not really a package, but software that is a customized memory allocator for Unix things like Linux or BSD. Right now we're focused only on Linux. Mike has a BSD version of it. We know how to do it on Windows, but that's a whole different story. And the idea is to replace the reason I'm interested in this again is because of all this fast SSD stuff that's out there now. And of course you could set up your swap space on SSD, and it turns out that Linux swap has improved dramatically, and that works out really well, better than it used to 10 years ago or 8 years ago when I first was experimenting with this. So this is actually a pretty viable approach for many problems. You could just set up a huge swap space on your fast SSD or Optane drive, and that just tends to magically work, except when it doesn't, it tends to badly not work. Like your whole system turns to just mud sometimes. Our little piece of code, it's a custom memory allocator called EXM, and it's a lot more flexible than swap. It's not a heavy hammer like swap. You get basically it replaces memory allocations with file maps, and it maintains a hash table of the mappings between the allocated files and the allocations. And it's very dynamic. You don't have to set up the swap space in advance and claim a certain amount of space. You just add files as you need to, and you have a lot of control over it through these controls like mAdvise, and there's lots of system calls that you can tune it with. we found that back a long time ago when we first started doing this stuff, before we let it sit, we found that they work really well together, letting swap handle tons of tiny allocations, which would otherwise overwhelm the memories in your computer, and let EXM handle single super large allocations for, say, like a big model matrix or something like that. And they just work, right? So you can have an R package that has some crazy C or Fortran or C++ code that you have, it's a black box. And it, from the standpoint of that program, it's just making a call to the regular memory allocation routine. We're intercepting that and replacing it like magic with this thing that maps out into files, right? So that stuff just kind of magically works. Here's an example that would fail. This is on my little crappy home PC, where I start up R with this EXM, load an R package that gives me some control over it. I set the allocation to, what is that? 100 megabytes. Anything larger than that will be allocated to a storage disk, an SSD that I've got. And then I just run stuff here. I run a QR decomposition. It runs slowly. It turns out that that's too slowly. There's a performance regression in the code that we haven't figured out yet. So this is kind of beta quality stuff. There's some issues there. But it runs, right? There's a lot of problems that we're still ironing out with performance there. But you can pretty much set this and run things. So that's the thing. It's up on GitHub. Again, it's very beta-ish. Only works on Linux right now. Soon it'll probably, I mean, Mike's working on it for BSDs, so that'll cover Mac. And we probably won't do Windows unless Microsoft really, they'd have to donate something to us for that to happen. And the other cool thing about this is it's not just for R. I mean, we wrote it for our use, which is R, because we do everything in R, but this works with anything. Python, Julia, I've actually used it with the GIMP to do super large images, actually, that would otherwise not work. So it'll just work with any program. But again, so will a super large swap drive. So like these two things are kind of overlapping, and hopefully I'm hoping to get them complementary so they work together really well. But right now, the performance isn't quite there for our thing yet. Then there's another thing that's even older. This dates back from 2005. And you can use this with EXM, this shim program. Shim is actually a Linux kernel module. It's really a file system that lets you present a large or small, a cluster of computers. It lets you glue all of their RAM together in a virtual pool of RAM that you can then use EXM to map into. So you can take a big cluster, like my cluster with 128 terabytes of RAM, and you can make every R program running on that cluster think they've got 128 terabytes of local RAM, actually, with these two things, which is pretty mind-blowing. And I've done crazy stuff like that, and it actually works. So these are really out there, not a normal R topic things, but they're kind of cool if you want to play with them. So there you go, a minute ahead.
You are allowed to plot in between.
So I'm the one with the 34 slides. Sorry about that. I'm going to do the best I can. I'm kind of a hobbyist here. How many of you have used TensorFlow? Raise your hand. Okay, good. Because I'm doing this in part to learn. So hopefully I'm going to learn a lot more from you than you're going to learn from me, but we'll see. Anyway, my name is Brad Banko, and I'm going to talk about what I've learned about how Google does machine learning using TensorFlow and the Google Cloud Platform. Do I do this?
You got it?
Oh, I think so, yeah, okay. This is from a course on Coursera that was just launched in May. Has anybody else looked into this course? It's a 5-week course, about 8 to 10 hours a week. And basically, TensorFlow is a library that allows you to specify data flow machine learning problems in a sort of platform agnostic form so that you can deploy them on systems like Google Cloud Platform, which will auto scale them based on the size of your data and your compute needs. Google uses this for a lot of its products, including continuous video analysis of YouTube videos, labeling, identification of images in Google Photos. And in fact, they say since 2012, this number is a little out of date, they've deployed about 5,000 TensorFlow machine learning models that are currently in production with Google, from language transcription, image and video analysis. They've developed machine learning APIs for video, image analysis that you can use in a toolkit, out of the box. And they do sophisticated things like identify faces and sentiments in pictures. They can identify locations. Pictures were taken based on landmarks that can be recognized in those pictures. It's pretty sophisticated stuff. The whole point of machine learning, adding it to your processes, is because it generalizes the problem and makes it more easy to personalize it to particular users' needs. So the example they give is that if you're searching for, a web search for giants and you're in San Francisco or New York City, you're probably going to get sports teams as a top result. But if you are somewhere else, you might just be looking for big people. So machine learning can take all those features, including your location stuff, into account. So TensorFlow is an open source software library for data flow programming. It doesn't actually generate output until you evaluate it. It generates something called a directed acyclic graph, which specifies how the data and the compute nodes are going to be related to each other. And then it marries right to Google Cloud Platform, which is an auto-scaling cloud-based storage and compute resource. So you don't really have to worry about your memory, for example. And you also don't pay for resources you're not going to use. So it kind of follows on that last talk a little bit. You don't have to fret as much about this. Now, I understand that sometimes those resources can be cost efficient. An example of this is BigQuery, which is a sort of an auto-scaling allows interactive analysis of petabyte scale databases. So for an example here, Medicare claims data from 2014 with hundreds of millions of rows, you can work with that interactively, which is pretty nice. Get results and query results back in seconds. They use a data set, which impresses me, as part of the lab for this course, which is taxi fare data from New York City. These are, I think, public domain data sets. It's got 70 billion rows, and this is, for the students taking this course, which is, to me, it seems like, does that seem pretty big to you guys for queries and machine learning? Lakshmanan is one of the instructors on this class. This is a sequence of the classes. Like I said, they're about a week, 8 to 10 hours a week, 5 weeks, 8 to 10 hours a week. They focus on trying to identify machine learning opportunities in your business and how to define them in terms of what you're trying to predict, what process you're trying to improve, what kind of API you might use, and what kind of data you want to try to collect. There's a manual phase where you have an individual working on the process, and then you delegate and try to expand it out and diversify it, and then you try to automate it, and eventually, ultimately, you do some machine learning, test the model, and ultimately you get it to a point where it will self-refine using the machine learning on a continuous basis. Their advice is don't try to make a fancy model, get more data, and maybe pick the right model for your data. And design your algorithms for machine learning around batch streams of data from the very beginning, because then you'll have an ongoing refinement and you can deploy new models periodically based on improvements. This is an outline of some of the processes and APIs that are available in the Google Cloud Platform. This cloud data flow allows for chunking, sort of automated chunking of your data, which kind of automatically scales, funnels it into your subsetting, and then your machine learning process. They use Python notebooks in Cloud Data Lab. In Cloud Data Lab, I think we're going to have a talk about Python notebooks today, but sort of who's familiar with Python notebooks? It's sort of a self-descriptive, self-documenting, executable format, sort of like RStudio and R Markdown, and Jupyter Notebook too. All of these Google tools are available in Google Cloud Platform for all phases of the analysis. It sounds like I'm doing a Google sales talk here, but I'm really not. I'm just kind of enamored by all this. These are some of the examples of APIs that they already have deployed. You can just run these out of the box. And like I said, they can do some pretty sophisticated things. With video intelligence, they'll label scenes, they'll detect shot changes, a whole bunch of stuff. You don't have to reinvent the wheel there. The TensorFlow API is divided up into 5 levels, starting on the bottom at a hardware level, then C++, and the core TensorFlow, which is Python. But for most applications, all you really need to use is TF estimator, the top level, because that's where you specify your type of model, the parameters on your model, your input functions, and your output in your application. Here's an example of some TensorFlow code starting with an imp. Can you read that? Is that too small? You import the TensorFlow library and you define a training input function. And this describes the features and the labels for the data. In this case, you are going to be predicting rents on house and apartment, houses and apartments. Can I keep going? Should I stop?
This will give you about 25 more.
Huh?
You got about 20 more seconds.
Okay, 20 more seconds. And so in here you can see, first you define the feature columns, and you see these prefixes for TensorFlow here. So you define the type of feature column you have. So it's a numeric column there, and there's a categorical column with vocabulary list. Let me just finish this real quick, this slide. Then you define the model down here using TF estimator. See, that's all you need. And the type of model you're going to use, which is a linear regressor. You input your feature columns to define the feature, and then to train it, you just invoke the training with the input function, the number of steps, and then you can get the predictions out. And this is creating a generator, I think it's called in Python. So, that's just a quick, simple thing. And maybe if I have time, I can go over a few more slides I have. But anyway, glad to be here. Oh, I should speed you up. TensorFlow, yeah. So we did this example, and then that's Lakshmanan, and he's just kind of demonstrating how when you create an expression or a data flow, it does not generate an answer, it generates the map, and then you have to evaluate it. And I think the purpose of that, and this is me just, is that allows at runtime for it to dynamically allocate depending on the size of your data and your compute needs. And this is an example of a map where the red squares are parameters and the round circles and stuff are compute nodes that the data is flowing through. One thing about the course is that you use Quick Labs, which gives you metered access to Google Cloud Platform, which is always more than you ever need, but it takes about 5 minutes to spin up one of these virtual machines. So it's a little tedious, and if you want to just play around and experiment, then it's a little frustrating. This is what the Cloud Data Lab looks like in Google Cloud Platform. You create the Data Lab virtual machine, and then you SSH into it. But then this is me just running one of these TensorFlow programs on my Ubuntu machine after installing the TensorFlow platform or modules there. And this I won't bother you with, but this was just, they're using pandas data frames to run through as the data input for a machine learning example or homework set. But this is the GitHub source for all the course material. It's GitHub, Google Cloud Platform, Training Data Analyst. And I think they just use a small subset of that, so they've got other areas in there. And then this is TensorFlow. You can go to TensorFlow and it'll show you how to install it on your own machine. And that's it. Thanks. Sorry.
Is anybody familiar with structural equation modeling? Okay. It's very social sciencey. So this is, very common like psychology research, that kind of thing. So Lavaan is the package I'm going to be looking at. That's actually kind of an acronym, latent variable analysis. It's called a beta package. I've never had a problem, and it's certainly a good alternative to a lot of the software that costs many thousands of dollars for this kind of proprietary boutique kind of psychology research. So I'm going to read in a data set here and do a demonstration of mediation. Relationship of self-esteem, of grades, and happiness. So again, very like education, social science kind of stuff. So read that in, change the column names. So I've got a little model picture here, and this will kind of read through what we're doing here. So we're looking at mediation. So what mediation kind of proposes is that we have what's called a direct effect right here between grades and happiness. You would think there might be some theoretical relationship between that, positive, higher grades, higher happiness. So what mediation proposes is that we actually have what's called this indirect effect right here. So this is all about causation and what we call like mechanisms. There might be some intermediary variable that's actually really influencing this relationship. So we're saying that this relationship of grades to self-esteem, then self-esteem to happiness, that's really the underlying mechanism that is really causing this positive relationship. So we're going to use Lavaan to actually set up this model and then test whether we've got mediation. So we're going to specify the model. In Lavaan, you're going to put this all in this quotation marks here. And the tilde looks familiar from regression. It's basically a system of regressions right here. These labels right here, if you think about like y equals mx plus b, this is kind of like the m. So what I'm doing here is setting up these regressions. And then down here, I actually want to label the parameters. So this equals and the colon right there is what's giving you the parameters. So I have the indirect effects again. When you're dealing with these two paths, we're actually going to multiply these regressions to get that total effect. So we've got the parameter there. We've got the direct effect, which is again that path from self-esteem to grades, or grades to happiness. And then I'm going to add these up just for ease of interpretation. So C plus A times B, so indirect, direct, and then total. So we've got our parameters here, we've got our regressions here, so this is our model. Okay, so we're going to run the model. Looks pretty familiar. We're going to fit the model to the data, and then we will look at the results. There are going to be a lot of results. I hope that we can kind of see these. But you can get a lot of stuff in here. Model fit, indices, things like this. You can kind of see how well your model is fitting. I'm not really going to get into that. I'm just going to look at the parameters here. We can get the R-squares, we can get standardized values, and so forth. So, okay, define parameters right here. I think this data is on a scale of 1 to 10. So essentially what this is telling us is we have our indirect effects, direct effects, and total effects. Not to rush to conclusions, but we see the p-values here immediately kind of indicating that the indirect effect is really kind of the underlying mechanism here. Estimate of 0.357, so basically we're saying that for every 1% change in grades, there's a 3.6% increase in happiness. And we can see, so what I'm going to do now is just show you if we were to not include that kind of intermediate step, that, up to the self-esteem and then the happiness. So I'm just going to rerun this, take out that indirect effect. Looks very familiar, but shorter. We've got the regression there again. We've got the direct effects. And then I'm just going to fit the model to the data again. And let's just keep going. Define parameters. So the estimate is very, very similar, but we have a significant p-value, so we're saying that this is really kind of a causal mechanism. If you didn't look at that kind of underlying, the happiness to self-esteem grades, this looks like a reliable model, but you're not actually really capturing kind of that underlying causal mechanism. So that's really the purpose of structural equation modeling. You can do things like factor analysis and systems of regression, path analysis, that kind of thing. One last thing here. I think I'm doing pretty good on time. Yeah, so that's good. There is a package that you can plot this. It can get kind of strange what you're doing. Sometimes structural equation modeling is kind of condescendingly referred to as spaghetti and meatball models because you have all these different, lines and the arrows and all this stuff. So it's kind of nice. I don't think that this is quite something that I would want to share or publish because it's kind of difficult to read. And as far as I could tell, I couldn't quite get this to draw in the way that I had it set up earlier. But basically what we're seeing here, we have this SEM plot library. So I'm just going to plot our relationship here so we can see the regression coefficients, and then these are the variances of these variables. So just something that, if you're working through a structural equation model, you can at least plot it and kind of visually see kind of what you're doing. So that's all I have, and I think I'm at about 6 minutes right now, so cool. Thank you.
Okay, I'm Ryan. Let's talk about Project Jupyter. So what is Project Jupyter? It's essentially an open source web-based development IDE. It's spun off from the IPython project in 2014. If you ever are Googling and looking for it, sometimes it's referred to in both cases, either Jupyter or IPython. It's very popular in environments where you're doing a lot of rapid prototyping, a lot of research, you're sharing results with your peers. It's a very powerful tool for that kind of work. There's 3 core applications to Jupyter. There's the original Jupyter notebooks. There is Jupyter Lab, which I kind of view as like Jupyter Notebooks 2.0. And then there's Jupyter Hub. Jupyter Hub's kind of out of scope for what we're talking about here, but if you want to use this across your entire team, you want to spin a server up, install Jupyter Hub, and work on the same OS, the same versions of Python or whatever language you're using, and libraries, you want to keep everybody on the same stuff. That's a very helpful tool to synchronize your team's workspace. Why should I use Jupyter Notebooks? Well, it gives you a really good platform to tell the story of your data using different types of code, visualizations, and Markdown. It's also very helpful for loading large amounts of data into your system and not having to keep rerunning your code and your modeling against that data and load it every time. When I first started doing some data experimentation, I was doing just simple Python scripts in IDEs or Vim or whatever it might be, and I found myself commenting out code and rearranging stuff to get things to work in certain orders. And when I started using a lot of Jupyter, you have like a cell at the top where you do a lot of data loading out of your CSVs or other data sources, and then you can do lots of experimentation on top of that data. And if you mess your data up, you go back and run that one cell, you now have a fresh set of data, you can move forward. Super helpful from a user experience kind of standpoint. And you can share and collaborate with others. One cool thing about notebooks is that you can actually execute all of the code cells in your notebook and then commit that state to a GitHub repo, and then share a link with somebody, and they can actually see all of your code, any markdown you use to describe the code you're doing, any output, console output from the application, from your code, and then also any kind of inline visualizations around that data. They get the full story of the data. You don't have to ship them off a Python script or some kind of other code and have them install different libraries, and again, get up to speed, ship them a CSV, they just start running. There's also a tool available on Jupyter.org where you can actually upload your notebooks and then share. You get a shareable link for that as well. MB Viewer as that tool. Okay, it sounds cool. How do I get it? Well, it runs on Python, so you got to get that. Lots of options how to get that. The recommended version on the Jupyter website is download and install Anaconda. Anaconda, if you don't know, is effectively a collection of packages around Python that bring scikit-learn and all kinds of other cool tools down to your system, including Jupyter. So it all kind of comes out of the box. You can also do it via pip, Python Package Manager, using that command right there. And that's it. It's just one command. It's either downloading Anaconda or installing via pip. And then you literally go to your terminal, type in Jupyter Space Notebook, and your browser will open up a tab to localhost 8888. And then you're off to the races. If you don't want to run locally, let's say your environment is locked down by your employer, or you just don't want to mess something else up, lots of hosted options you can look into. AWS EC2, if you ever heard of their deep learning AMI, a lot of folks, we use it at my work for training models, both in tests and experimentation and in production. And that actually comes with Jupyter pre-baked onto it. And then actually, I didn't know this until I did a little bit of reading, but recently Kaggle actually has what they call kernels. And you can do a notebook option for a kernel. And a few months ago, they actually announced free GPU time on your Kaggle kernel. It's no 5,000 core server with 100 petabytes of memory, but it's a K80, so it's a cool, terabyte, excuse me. It's a cool option to look into if you want to use that tool for some free GPU time. But can I use R? Well, yes, you can. You can actually use dozens of languages. Jupyter considers a program language a kernel. They call separate things kernels, and you're running inside the kernel. Core languages that work with inside of Python, Jupyter Notebooks, or Python, R, and Julia. And I actually did this locally. I was playing around with R in my Jupyter Notebooks, and it was pretty straightforward to set up. I went into our studio, went to a console, and just I found this online. I linked this at the end of the slides. Installed some packages. I ran DevTools installed from GitHub. This is not a package on CRAN. I had to actually install it from a GitHub repo, and then ran on install spec, and I was off to the races. I ran Jupyter. This is actually Jupyter Lab, but I got a little R button to make a new R notebook, which was, pretty straightforward, like a 5-minute job, and I was good to go. Cool thing here as well, I also got an R console in a web browser. So if you ever want to shop into a console, you can do that through this tool as well. Pretty basic sample. Starting at the top here, the first cell there is actually Markdown, just a Markdown header. You can use that to kind of describe what you're doing in this code. I'm just printing hello world. And that next code cell, and then below that, the line 1 is just the console output, echoes back to you. A little more advanced, you can run ggplot right inside of a notebook. You can actually install the package directly. I loaded it. I'm using this iris data set built in, and the one-liner to call the plot command to generate the nice inline plot. I had to cut it off for the screenshot here, but you could send this off to somebody, and they could see this without having to push or run anything. They could just load this up and view your results. So Jupyter Lab, like I said, 2.0. One horrible thing about Jupyter Notebooks is that if you're doing a lot of experimentation, a lot of different notebooks, they end up all over your desktop in different browsers, different tabs, and you're trying to find version 1.0 or version 2.0. And it gets a little unwieldy. I really love how they brought it into everything is tabbed in your browser. You get a nice little file explorer. You can do lots of different things here. You can move things around and locate the panels how you want. I'd look at this and think about if I was training a machine learning model and I was trying to see the code I was training with, see some of the output and some of the charts of the loss functions and et cetera down below. It gives you like a one-stop shop for all of that. But maybe it's not always that great. Put a couple blog links on here. Take a look at them if you'd like to. There's kind of two schools of thought. Some folks really love Jupyter. Some folks really not so much. I kind of boil it down to engineers versus stats, scientists, folks in that camp. If you want linters and autocompletes and all of those great things, maybe this tool isn't for you. Maybe there's other IDEs, other options for you. If you want people to collaborate and load lots of data and share with your fellow coworkers and all of that stuff, maybe this tool is a better one for you. And one of the blog post authors actually mentioned R Markdown as an option to take a look at as well, as an alternative to a notebook. A couple of references here if you wanted to download any of the stuff I use to set things up and get it running locally. Thanks for your time.
All right, let me get my timer going. All right, so my name is Jim. Today I'm going to be talking about the bench package, which I guess is a new take on benchmarking. So first, I want to talk a little bit about why you might want to benchmark code. So benchmarking is basically comparing two expressions of code that do the same thing, but maybe do it in a slightly different way, one of which may or may not be faster. And often when people are talking about benchmarking, they'll bring up this quote by Donald Knuth. Says premature optimization is the root of all evil. And usually when people bring up this quote, they're basically saying that you shouldn't try to optimize your code. It ends up making it harder to read, harder to maintain. But if you actually read the paper where this comes from, Knuth also goes on to say that a good programmer would be wise to look carefully at the critical code, but only after it has been identified. So basically he's saying you shouldn't not optimize at all, but you should make sure you know exactly where you need to optimize before doing so. And also he says that tools should be designed to provide us with feedback indicating what parts of our programs are costing the most. So once you know exactly where in your program the bottleneck is, you need to figure out how to make that faster. And that's where benchmarking comes in. So the bench package has a function mark, so you can call benchmark. And the way this works is up at the top, I'm calling the function, and then I give it 3 different expressions that I want to benchmark. All these expressions are basically just subsetting a data frame. And then benchmark will then run each of these 3 expressions a number of times and time each of those runs. Then I'm returning the result and it returns the results in a data frame. So then I'm printing a couple of the columns from that data frame, just the expression that was run, the minimum time of the fastest, basically that's the fastest run for each of those expressions, and the amount of memory that was allocated during that expression run. And also the last column is the raw timings for each run that was performed. And a couple things to note here are that the times are given in human readable formats, so you get the units of the time like in the display, and as well as the memory allocation. So it makes it very easy to see exactly the scale of your times. And that's really important for expressions that take widely different amounts of time to run. If one is only taking microseconds and the other is taking full seconds, you definitely want to be able to see that. But if you use just raw numbers, in those cases, it's hard to compare the results. Yeah, okay, so other things that the package gives you, so it always uses the highest precision timers that the OS provides. This is often in nanoseconds. It automatically compares each of the expressions results for equalities. So if you make a mistake and the expressions are not actually doing the exact same thing, then it gives you an error, so you know that up front. It uses adaptive stopping instead of running each expression for a given number of iterations, it runs each expression a certain amount of maximum time. So it says basically for like half a second, I'll run it as many times as I can. And that's useful, again, if your expressions take widely different amounts of time. You don't want to be spending tons of time on the very slow expressions. And then lastly, the benchmark package tracks R's garbage collections, so it per run, so it knows exactly which runs had a garbage collection in them. And the plot over here is showing that the red points are all the runs that had no garbage collection in them. The green points are the runs that had a level 0 garbage collection, and this little purple point is a level 2 garbage collections. So you can see, at least in this example, garbage collections are very costly operations. So being able to tease apart the effects of when something is slow because it had a garbage collection in it, or if it's just slow because of the actual expressions that are being run. So another function in the bench package is called bench press. And this basically allows you to run a benchmark on a grid of values. So here I'm calling bench press with two inputs, the number of rows and the number of columns. And what bench press does is expands those values to the full grid, so you get a 4x4 grid of all the possibilities between those values, and then you put your benchmarking code inside that. So basically what this code is doing is taking the rows and columns, creating a new data frame of that size, and then running our previous benchmarking code on it. And then when we run this, we get the 12 possibilities, all of those 4 combinations, which each of our 3 expressions. So this makes it very easy to test a given set of expressions on a wide variety of input sizes. So the last thing that the package gives you is extensive plotting support. So this is again taking our same result object, and then we're just calling the autoplot function, and this is the package provides a method for the autoplot generic, and this basically gives you this plot on the left, just this autoplot call. So you don't have to do a lot of extra custom ggplot code to do this. It gives you sort of nice output by default. And so it gives you this faceted output, which is based on the inputs to our press function. So we can again see the columns and the rows here. So we get our 4 faceted plots, and then again each of our individual runs is colored based on whether it had a garbage collection or not. So the autoplot function also has a type parameter that lets you do other types of plots. So in this case, this is a violin plot or a ridge plot that you can do just with this autoplot and the 1 parameter. You can also do custom plotting. So I mentioned earlier that the objects all have their full data inside them, so you have all of the raw data. You can use all of the tools that you're familiar with to manipulate data frames to extract this data and the new plotting on them. So here I'm just taking my results, unnesting them to expand all of the list columns into their full set, and then filtering, just taking out all of the runs that had a garbage collection, and then plotting the memory allocation and the time. And one thing to note here, and I didn't point out earlier, was that the times are nicely scaled for, like the scale labels you get are human readable, and that's also true for the memory allocations as well. And that's my last slide. So if you want more information, go there.
So this is going to be a very basic talk. I'm surprised sometimes the number of folks that don't know about Rprofile, so I thought that would make a good brief topic. So what is the Rprofile file? It runs on startup. So for those of you familiar with, so for example, setting up your bash shell, the bash rc file is a similar equivalent to what you're going to be doing with Rprofile. So I'm just going to focus on that for this talk. However, this would be used for sort of light configuration. If you really get into heavy startup configuration, there is a package called startup that's worth looking at as well. That lets you, the best equivalent I can give is anybody using the Z shell. There's a common package or piece of software called OhmyZSH, and it has like a series of like plugins and file conventions and directory conventions for how you set up a lot of shell configuration. That's kind of what the startup package brings in. So what can you do with Rprofile? Anything you want to do in R. That doesn't mean that it's a great idea. So what should you do with Rprofile? For start, we talked about configuration, things like picking a default crayon mirror. So anybody who's just installed and fired up R, it's going to ask you, what kind of crayon mirror you want to connect to. These type of things can be set up to get out of your way. You can customize the prompt. So literally the REPL shell at the end of it, just like you can with a bash shell or other Unix command line shell. You can figure how numbers display. So this is a common one that I like to set up right away. And set any personal info for packages that you use, packages that require email, these type of things, or that you put a name in. So things to avoid in Rprofile. So anything that's going to cause unexpected behavior or clutter up your namespace, right? So if you're declaring a bunch of functions or global variables in there, like largely you should put that code into a package, and then you can use Rprofile to load up packages that you want loaded by default. If you were someone that always uses the tidyverse, you could put in your Rprofile library tidyverse, and then there you go. You're just going to have it there available all the time. In general, though, the point I'm getting at here is that you wouldn't want anything that if you're troubleshooting a single R file and a programmer comes along to assist you, they shouldn't be surprised by anything that got loaded behind the scenes. Lastly, I mentioned they're introducing startup latency. So anything that connects to the network, right? Like auto updating packages or those kind of things. Then you go to a coffee shop, you don't have Wi-Fi, you fire up R, and you don't know why you don't get a prompt right away because it's not getting to the network or these kind of problems. So what does an example of an Rprofile file look like? This is mine. You can see I don't do a ton in it. In the top here, some options are more complex structures. So like your repository settings is a list. So the easiest way here is to get that out as a set of options, set the options you want to set, and then you're passing it back in here. You see as the repository equals R for that object. The whole thing is within a local function that just creates its own environment. And so anything that's declared in there is not going to be seen in scope if you did an ls to list your variables. As an example there, that R local variable, if I fired up an R prompt, you would not be able to see that. So next, if interactive, this isn't really that important or going to come into play a lot. I just want to show it's possible that that would only run in situations where you're going to the REPL. If you're doing a shelled out headless command, that's not necessary. But within that, you'll see that's where I'm customizing the prompt. I'm showing how many significant digits to show, the threshold for scientific notation, etc. And at the bottom here, we're showing an example of DevTools is something that will regularly use your email and your name, and so you can just have that pre-configured so it's ready to go. What happens if you break stuff in there? That is not good, right? To crash your R right before you start. So if for any reason you were to have complex code and you're trying to figure out what's going on with it, you can seem tough to debug. Just make sure you set the option so that any error causes your debugging browser to kick up, and then you can figure out what's going on wrong. So just put that at the top of your Rprofile file, and that will bail you out of these kind of problems. And that is it. So next we have Walt.
So I guess the guys who wanted to do machine learning on Google Compute needed lots of slides. So this is a follow-up on what Brad was doing. I'm going to move as fast as I can and do the micro machines man thing. So this is image classification, deep learning using R, Keras, TensorFlow, and GCP. Deep learning is a great way to deal with highly dimensional data. What I tried to do here was actually build a convolutional neural net using all of those above tools. We'll explore the tools a little bit. What's out of scope? Transfer learning is a hugely important concept in deep learning where you would take an existing model and then put it into this new space. You would take the weights that your model had already learned and reuse those. I wanted to just learn how to do this because I didn't know how to do this yet. So I wasted a bunch of electricity in Google data centers. That was the approach I took and basically rebuilt models that were already way better than mine. So sort of state of the field. Jeffrey Hinton and Jan LeCun are huge figures in the field. They've done a lot of work in both CNNs. Jeffrey Hinton just introduced some really interesting concepts around capsule networks. What a lot of this is a book that came out in early 2018, Deep Learning in R. JJ Ayer, I may be butchering that. He's probably your boss-ish. Francois Chalet. They wrote an incredible book on how to do this with a Keras package and then a Cloud ML package, which basically easily makes it so you can just submit R jobs with a couple of parameter files and then go get a cup of coffee, wait a couple of days, however long your model and however much data you're running, and then come back and get tensor boards to train. So what we did, the data set it's a popular benchmarking data set. It's the ImageNet data set. You see sort of an example of what would be a class porcupine. A bunch of different images of porcupines. For this, I ended up using, Stanford put out a tiny ImageNet data set, which is 200 labeled classes instead of the full, which is 1,000. The original is 150 gig. This one's only about a gig, so it's a little easier to manage.
What we wanted to do here is predict top 5 accuracy. What that generally means is, an image could have a porcupine and a bat and a cat and all kinds of different things in it. So you want your classifier to be able to pick out multiple things and then return 5 things that it thinks are in that picture. And if any of the 5 are the actual ground truth, we'll consider that to be accurate. What we're using here again, TensorFlow, sort of a nice interface with TensorFlow that's user-friendly is Keras. We're using R and we're using GCP's Cloud ML, which is really nice. I think this is a pretty early 2018, late 2017 when they really started making it popular. If you're not familiar with what a convolutional neural network is, we won't go too far into deep learning, but the idea is you would put a number of hidden layers. You would feed forward your data through the initial input layers. You would train weights internally, and then at the end you would have an output layer that would have your classifier. In this case, this is our top 5 accuracy. What do you think is in these images? And then you backpropagate to retrain those weights once your algorithm understands what the ground truth is. What's cool about convolutional neural networks is they basically create a sliding window so that in an image, an ear of a cat may be in the upper left quadrant or it might be in the lower right quadrant. And this, they'll create sort of a sliding window that understands what a semantic representation of an ear is and then can find it anywhere in that image. Since images aren't the same size, they're not shaped the same, but you still might want to see certain things in a given image. That is the wrong direction. So here's an example of what using Keras in R, a model architecture might look like. Here we're using a Keras model sequential. I basically just kind of did 2 simple models that were based on 2 highly performant models, AlexNet and ResNet, and then did some hyperparameter tuning within those models and then just kind of benchmarked to compare them. So here you see a convolutional layer interspersed with a max pooling layer, interspersed with a convolutional layer, etc. We flatten those out toward the end. We do a dense layer, a dropout, and then we put a softmax classifier at the very end, and that's sort of our output. And that's sort of a representation of what you see up in that top middle. Here we're doing things, the Keras packages allows us to do great things like define whatever our accuracy metric we want. In this case, we're doing top 5 accuracy. We then compile our model. Again, this uses all the nice pipe Magritte things in R. We define how we want to optimize and retrain through backpropagation. And then because in larger deep learning it often relies on models that will not fit into memory, the Keras package and the R package have these great methods for data generators where you could just batch sample from, in this case, a Google Compute bucket where all of your data is. In this case, I've got all my images sitting in a bucket. I go grab however many I want and then pull them in and then train those. I also do the same thing with a validation so that way I can predict against both my train and my validation to make sure I'm not overfitting. And then you train it and run it. What's nice about Cloud ML is basically you could store all of that in a single R file. You see here I've got little flags, and that basically references a separate YAML file where I'm then creating variables that get called in and pulled in when you do down here your submit Cloud ML train my job. And then any YAML files are in that same directory, and those YAML files can specify hyperparameter tuning, flags, things like that, but they can also do cool things like I want to use a M2 extra large. I want a double large GPU. You can sort of specify some of the hardware parameters. And that in particular is what is really nice about this Cloud ML package. I don't have to spend time spinning up images, either putting Docker into them or putting all the packages I need in them. You just submit this job, don't think about the hardware, and come back later and see what you got. So in this case, before we get there, we did some tuning tricks. There's a number of things that you can do in deep learning to improve your model. One that you see pictured here is data augmentation. That's the idea that you would multiply the size of your data set by doing simple things like skewing the image, flipping it, moving it left or right, and that way you're basically learning on the same data. You don't have to increase data generation. Dropout is something really possibly controversial. Jeff Hinton's group both created it and also possibly are denouncing it at the same time. It's basically when you're going through and doing modeling, forget random things. You basically are telling your model, hey, just forget all that stuff you learned. Forget 30% of it. ignore those values. So that's, you know, kind of counterintuitive, but it does prevent overfitting, which becomes important in some of these large data sets. I seem to be missing an image here. That's my bad. We had 4 different models that were visualized here. Showed sort of the general performance of those. Did top 1, top 2 accuracy. One of the nice things again about CloudML is basically you can collect your tensor boards, since this is running over TensorFlow and Keras. So you can just pull down with a quick call in your RStudio or wherever you're running this. Give me the tensor boards, you get those logs, and then you can actually understand what was happening in any given training run. So here you see sort of those 4 that would have been described in this slide visualized. We have along the x-axis the number of steps that were run. So a step would be show the model your entire data set, and along the y-axis we see the top 5 accuracy. You can use tricks like early stopping. I think that's maybe one I didn't do here, so that's why some of these have different run lengths, where we hit a certain accuracy and then chose to stop. So small-ish data set, again 1 gig, but we got a reasonable top 5 accuracy. Thanks.